Hello everyone, welcome back to Labtube. In this video I'm going to do question 3 of section 16.8. The question asks to use the Stokes theorem to evaluate the surface integral of curl of FDS where the vector field is z e to the y first component, x cosine y second component, and xz sine y as third component. And the surface is the hemisphere, x squared plus y squared plus z squared equals 16 for positive y's. And it is oriented in the direction of positive y-axis. Okay, so what you need to know is Stokes theorem, basically. Stokes theorem says Stokes theorem says that if you have surface integral of curl of a vector field, not the vector field itself, the curl of vector field, then it is going to be equal to the line integral of the vector field itself along the boundary of the surface. Okay? So surface integral into the line integral. But there is one thing you have to notice, and it is that when you are integrating a vector field, either on a surface or along a curve, you have to fix an orientation. Okay? And this equality is true if the orientation of the curve, the boundary, is positive with respect to the orientation of the surface itself. Okay, I will discuss that in details. Note that if you miss this point, you may get a number which is off by a minus sign. So you're supposed to get positive, then your result would be negative, or the other way around. So if you don't check the orientation and you don't choose the right orientation, your answer will be off by a negative sign. Okay, so that's the general fact, that's the Stokes theorem, but what about this case? So let's see what is the surface. So I have x, y, z. It is a sphere centered at origin, and its radius is equal to 4. So I'm going to have a sphere, and I'm just taking half of it. But which half? The half for which I have positive y's. That's my sphere, that's my hemisphere. Okay, that's my surface, S. And what is the orientation? Orientation of the surface is in the direction of positive y-axis. So it is going to be of this form, like this. Okay. First thing to find is the boundary of this surface. So boundary of the surface is the set of all points at which you cannot continue going in 2 dimensions. So basically, if you start from this point, you can move this way, that way. Yes. But then when you touch this part, this line, the end part, that is going to be the part that you cannot move in 2 directions. So you stop at some point. Those points are the boundary of the surface, which I show you here. But what is the description of those things? So you can get that description by this fact. This is sphere, and you just taking y bigger than equal to 0. At y equal to 0, so y equal to 0, the boundary happens at that point. So if you set y equal to 0 in this equation, that's the boundary. So basically intersection of y equal to 0 and the sphere. It is going to be of x squared plus z squared equal to 16. It is a sphere as we expect, it is a circle as we expected. If you cut sphere by a plane through the origin, through the center, then you will get a circle. Okay? And that's the equation for that. But now you have to ask me, what is the right orientation? What is the positive orientation for this? Positive orientation. Consider yourself as a person walking on the surface, on the boundary. But you take the orientation of the surface to be the up. So you walk like this on this sphere. It's like we're walking on the earth, the sphere which is earth, yes? So we are walking like that. Then when you have to consider an orientation, when you move on that orientation, the surface stays on your left. So if this guy moves to this point, so if I go from this to that, as you can see, it's like this, and I go down, the sphere, the hemisphere stays in my left. So it is here. It is in this guy's left hand side. That means this is the right direction. So this is the positive direction. Okay, let me draw it here. I have to be careful because you see this is z-axis, this is x-axis. How should I put them? I should put them like this. Z is this, x is this. Yes, because I want to get the standard axis. So if that's the case, I have the circle. As I move from here to here, I'm moving from z-axis to x-axis. So this is the orientation. Okay, that's good. Now we found the boundary, we found the positive orientation of that boundary. Now we have to find a parametrization for that. So parametrization for boundary. So I want to now parameterize this curve, yes? What is it? It is a circle of radius 4, as we have there. And I want to parameterize it. So remember that we parameterize circle always using the polar coordinate, r theta. But in this case, note that we replace x-axis by z and replace y-axis by x. So in this case, we are going to have r cosine theta for z and r sine theta for x. Okay, so let's just put everything here. And we know that r is the radius of the circle, so it is going to be 4. X is 4 times sine theta, and z is 4 cosine theta. You have that? What about y? There is no y here because we use it here. Y is equal to 0. This happens in zx plane, which means y is equal to 0. So it's there. And then what happens to the boundaries of theta? We know that to go around circles for one time, we have to go from 0, theta from 0 to 2 pi. Okay, that's great. Now we can use the Stokes theorem. The Stokes theorem says that if you're trying to find curl of f, surface integral of curl of f on a surface S, you can do it by finding the line integral of f itself along the boundary of the surface. But how do we evaluate line integrals? To evaluate line integrals, you have to parameterize the curve, which we did here. Then you go change three things. Boundaries for boundary of the parameter. Plug in the parameters in your vector field. For dr, you find r prime, it's a vector, and dot product it to your vector field, and then you get a function integrate with respect to your parameter. Okay, now let's apply all these things. 0 to 2 pi, that's the boundary. For vector field, I have to plug in, for x I have to plug in 4 sine theta, for y I have to plug in for z I have to plug in 4 cosine theta, for y I have to plug in 0. So here, z is 4 cosine theta, then e to the power y. E to the power y is 0, so e to the 0 is 1. So the first component is 4 cosine theta. Second one is x. X I know that is 4 sine theta. And cosine y. Cosine of 0. Cosine of 0 is 1, so my second component is going to be 4 sine theta. Okay, and for the third one, I have sine of y. Sine of 0 is 0, and you multiply to the other things you can see. That's my vector field when I plug in the parameter. Okay, what about the derivative? Derivative of the parameterization. Derivative of sine is cosine, so first component is 4 cosine theta. Derivative of 0 is 0. Derivative of 4 cosine theta is negative 4 sine theta d theta. This is great now because if I dot product these two, I'm going to get a function in theta, and this is going to be an easy integral. It is just regular integral. So let's multiply this to that. It is 16 cosine theta squared. Second component 4 sine theta times 0 is 0. Third component 0 times something is 0. So that is my integral. So I have 16. Let me put 16 out. And to evaluate integral of cosine to theta, we always use the double angle formula, which tells us that cosine squared theta is equal to 1 plus cosine to theta over 2. So I have 2 divided by 2. Okay, then I get 16 times antiderivative of half is half theta, and antiderivative of cosine 2 theta is 1 over 4 sine 2 theta, and we go from 0 to 2 pi. If I plug in 2 pi in sine, I'm going to get 0. If I plug in 0 to sine, I'm going to get 0. And then the only part which remains is this. 16 times half is 8. 2 pi minus 0, which gives me 16. Okay, very quick wrap up. Stokes theorem says that when you're trying to find surface integral of curl of a vector field along a surface, you can do it by finding line integral of that vector field itself along the boundary, but you have to be careful about orientation. We found the boundary of the surface, which was circle, and we parameterize it in right orientation. It's positive with that orientation. And then use the Stokes theorem. We got a line integral. How to evaluate line integral? We did these 3 steps. Boundaries, plug in parameters in your vector field, and dr is r prime. We plugged in everything, dot product, we get a regular integral, we integrated, and we got the result, which is 16 pi. Okay? And thank you for watching this video.